Good. I apologize about that. Welcome back to fluid mechanics. I found my other set of markers. Last year, well, I think it was Hayden. Uh, they knew that my fluid students, they knew that I like different color markers, and I didn't have them on me. So one day I come to class and I have this beautiful box with a bunch of markers with double heads, and I to this day I don't know who bought them. I accuse Hayden of doing that. He says he didn't do it, but he wouldn't tell me. He wouldn't reveal the identity of who did. So but I'm thankful. So I found that I found all of those in my little kit, and all right, we're back in action. Some of you have been have had questions about the homework, specifically the last problem, and some of you met with Hayden. Some of you tried to meet with me. We exchanged emails, etc. And the struggle seemed to be with the integral. Oh, this one doesn't work. I'm going to throw that away. Seemed to be with the integral of p n ds over the surface of the cylinder. So just to clarify to you, this cylinder is immersed in a fluid. Okay, so there's flow going over it, and that flow is exerting a force on the cylinder. And your goal was to compute the net force on the cylinder. And the net force is going to look like this. The forces on the surface of the cylinder are going to look like that, right? So P is a scalar, but once you specify a surface, it automatically becomes a force. So this is Pn, okay? It is acting on the surface of the cylinder. Now you take a cross section, you assume the depth in the z direction is 1 or whatever L. This integral is going to calculate whatever is in the integrand over here is going to calculate the force on a small area, okay? Now, some were struggling with how you define ds. You've done that in your physics class, okay? When you look at this from this side, assuming unit depth, okay, this is ds, this becomes ds over here. And if this is the center of the cylinder, and this is the radius r, then ds is simply the arc length, okay? What is the arc length? R times theta. In this case, it's just a d theta because it's an infinitesimal one. So ds is simply r d theta, okay? The force in the x direction is the projection of the net force on the x-axis, the force in the y direction, the projection of the net force on the y-axis, okay? So f cosine theta, f sine theta, okay? We'll get to solve this problem at some point. But it's probably a good reminder for things that you might have forgotten from your physics, etc. But there's going to be a lot of stuff like that in the class. I don't mind you using online calculators. I know some of you did that. I don't care about that. Use Mathematica, whatever. But as long as you can formulate the integral, okay, appropriately. Okay, last time we derived the infamous Reynolds transport theorem. Where is it? Okay. And that is one of the most important equations that you want to keep in mind. Okay, we're going to rewrite it over here. We'll use black. Okay. For an extensive property. Not working. Okay. For an intensive property B equal to the integral of rho B dV, where B is the intensive property, the lowercase b. This is intensive, and this is extensive. Okay. Then the Reynolds transport theorem tells us that it relates the system description, you're moving with the fluid, to an Eulerian description. Tells us that the rate of change of the extensive property on the system, dB by dt, which is equal to d by dt of the integral over the system of rho b dv, okay, equal to partial by partial t integral over a control volume. You choose an arbitrary control volume, okay, rho b dv, plus the integral over the surface of that control volume. So CS and CV there are related to each other. CS is the surface, or the surfaces of CV. Rho b u and ds. Okay. So from here onward, we're gonna take each one of those great conservation laws. We're gonna identify what the extensive property is, what the intensive property is, and use the Reynolds transport theorem to derive the governing equation that results from applying that law. First step is mass conservation. We did that last time. We'll redo it again. So, mass conservation. In this case, B is mass, M, or mass, which is the extensive property, and lowercase b is 1, the intensive property of mass, okay? Because you already have rho over here, so b becomes 1. In other words, mass is integral of rho dv, okay? So in this case, what you get for mass conservation, we know that dm of the system by dt is equal to 0. That's the law of mass conservation. Law of conservation of mass, okay? That translates to d by dt of the integral of rho dv over a control volume plus the integral over the control surface of rho u dot n ds equal to 0. Okay? Agreed or disagreed? Agreed. Okay. Let's do a couple of examples now. So those examples are taken from undergraduate textbooks in fluid mechanics, but it's good to revisit them now, you know, and apply this mass conservation law. We'll start with example 1. Example 1. Okay. Consider a pipe or a hose, firefighter hose. Okay. So you got this kind of strange looking hose, kind of bendy, etc. Okay. Cylindrical, doesn't matter. Okay. Okay. There's water coming in and water coming out. Okay. Suppose that the inlet area over here is A1 with a diameter D1, And the section over here, it's got an area E2 and diameter D2. The question now is to relate, and suppose that the flow over here is coming in at a velocity v1, coming out at a velocity v2. Suppose the velocities are uniform. Okay, for simplicity, suppose the velocities are uniform. Okay. Now the question is find a relation between v1 and v2. Find a relation between v1 and v2 using mass conservation. That's all you need, really. Think of v1 and v2 as the average velocities at the inlet and the outlet, respectively. Okay. We kind of know the answer, that v1a1 is equal to v2a2, but let's just run it through this mechanism and see how that works out. Okay. So we apply the law of mass conservation. First, we need to define, so let's just write it down, d by dt of integral of a control volume of rho dv plus integral over the control surface of rho u dot n ds equal to 0. Okay, so we need to define a control volume and a control surface. We can simply just draw the control volume around, that's completely arbitrary, it's up to you. I would always choose the control volume such that it simplifies, it has the important surfaces that I need, which in this case are the inlet and the outlet. But the other surfaces, I chose them where there's no velocity coming in or out, so that rho u dot n is equal to 0. So the surfaces on the side of the cylinder, these surfaces on the side, there's no velocity going in or out, so there's no flow through them, okay? We're gonna assume steady state, so, and really density is constant, in this case, water, so this is 0. So all you have is to do this integral over the control surfaces. So the control surfaces that are of relevance, like I said, is this one, S1, and that one, S2. Because over here, u dot n is equal to 0. There's no flow going in, okay, or leaving the surface, okay? Because it's an impermeable hose, right? There's no velocity, the fluid cannot go in or out of the hose. So that leaves us with this, only with this integral, the integral over the entire control surface of rho u dot n ds, which is equal to the integral over surface 1 of rho u dot n ds. So in this case, it's going to be u1, correct? Because that's the velocity at surface 1, plus the integral over S2 of rho u2 dot n ds, okay? And that's equal to 0. Now, u1 is constant and rho is constant, so they can come out of the integral. But there's also one little simplification you can make, is that say, well, you know, u1 dot n, so u1 is going in, or v1, right? And n is in the opposite direction, so u1 dot n is simply minus v1. Agreed? So this integral gives you rho minus rho v1 times a1, okay? Plus, now this integral u2 dot n is simply v2, right? Because n is aligned, is always pointing outward, okay? So u2 dot n is simply equal to v2, right? So then the integral is simply rho v2 times a2. That's equal to 0. Okay. Now rho and rho can simplify, and that gives you v1 a1 equal v2 a2. Okay. So now this is why the flow goes faster when you squeeze the end of the hose, because V2 is equal to V1 A1 over A2, okay? If A1 equal to A2, so the same area, then the velocities are the same. But if you reduce A2, right, if you squeeze the hose at the end, then V2 is going to shoot up, okay? All right. Now let's do an example where we can see some time dependence. So this Reynolds transport theorem is really useful to doing this kind of analysis, integral analysis. It didn't help us at all in finding what the velocity profile looks like, for example, right? How the velocity might change inside the pipe. So that's where the differential form becomes more useful. But the integral form is another side of the differential form, and we'll see how they're related. But it's really helpful in doing this kind of analysis. This is the zeroth order analysis that I would do on any fluid problem. Just look, the entire system, see what's going in, what's coming out, draw a couple of conclusions, and then, move on to more complex analysis. Okay. Example 2. You have a little tank. Okay. Let me see. See how we're going to draw it. You have a tank, and it's connected to a hose over here. So there's some water coming in over here at a velocity v1, and this is the area. This area is a1, and there is water coming in, and clearly the water is going to start filling up the tank, right, as you bring in more fluid, and there's some air trapped over here. Okay, the area of the tank is a tank, so this is the kind of the area of the tank. You can assume it's cylindrical, rectangular, it really doesn't matter. Okay, now as you fill in the water, right, there is a height for the water that's a function of time. So the question is, what is that? How does that height of water change with time? Okay, right, so we will find, question would be, find h of t, right? So we got water, we got two fluids over here. This is water. We're going to say this has a density of rho water. This is air. This has a density of rho air. Okay. To apply the integral form of the mass conservation, again, we're going to take our equation d by dt integral over control volume of rho dv plus integral over the control surface of rho u dot n ds is equal to 0. Okay. So next step would be to define a control volume. What do you think? How about I just take this control volume over here? I want my control volume to be fixed, okay? Because I don't want it to change over time. If I had chosen the control volume to contain only the water, then that control volume is changing over time. Is going to mess up this derivative. Makes it a little bit harder to deal with, okay? Because then the volume itself is changing over time. So, you get into a little trouble over there. Instead, I pick a fixed control volume, which is all the entire tank, okay? So now we start with the time-dependent integral, d by dt, integral over the control volume of rho dv. That's necessarily equal to d by dt of the integral of the control volume of water, okay? Rho water dv water, well, dv, right? Plus d by dt of the integral of control volume of air, rho air dV. So in the end, I ended up splitting the compartments into a water control volume and an air control volume. Now, what does this integral designate? This is the mass of air, right? This thing is the mass of air. But the air is trapped. So the mass is not changing in time, right? It just gets compressed. So the integral, this integral simply is evaluating the mass, this mass over here. It doesn't change over time. It's the same mass of air, right? Once you start putting the water in, you trap that mass of air, you're not changing it anymore. So this necessarily is 0 because mass of air is constant. Okay. Now this one, rho water is constant, and the volume, so it becomes a d by dt integral of dV, which is the volume of water. What is the volume of water? So we get a d by dt. Let me change the color. We get d by dt of rho water, which is constant. We're going to pull that out, times the volume of water, which is rho water d by dt. What is the volume of water? It's the area of the tank times the height of the water. So A tank times H of T, which is simply, because A tank is constant, you get rho water, A tank d by dt of H. Now I switched from partial derivative to a ordinary derivative because H is only a function of time, okay? Don't confuse this d with the other d of the system. We're going to change the nomenclature later and use the material derivative form. What do you think so far? So we got it, really. That's what we're after. We're after some equation that governs how H changes over time, okay? Now for the second integral over the control surface of rho u dot n ds, okay? What is that? The only relevant surface that's bringing in fluid is this one. We call that, let's call that S1, okay? It's this surface, S1. So that's really equal to the integral over S1 of rho water, u at the surface 1 dot n ds. Now u1 dot n is minus v1, right? Because v1 is coming in, and 1 n is in the opposite direction, so the dot product is a negative v1. Rho water is constant, v1 is constant. This integral turns into just rho minus rho v1 times the area. Okay, so that's minus rho water v1 times a1. Okay, now you combine the two, you get d rho water a tank dH by dt minus rho water v1 a1 is equal to 0. Sorry, minus rho water. So rho water simplifies, and we get dH by dt is equal to v1 a1 over a tank. And simply h of t is v1 a1 over a tank times t. Okay, so you get a linear change. Okay, if you plot h versus time, h changes linearly, and the slope is v1 a1 over at. Okay, not the angle, just the slope is, confuse the angle. Okay, v1 a1 over at. That's nice, huh? Okay, we'll do one more example on the integral form of mass conservation. Example 3. So last time we ate some popsicles in one of the examples we had. So assume that you still have one of those popsicle sticks, okay, with you. And now one of your neighbors gives you a can of honey, Utah honey. So Utah is super popular for its honey. It's the bee state, beehive state, right? So there's the beautiful bumblebee. If you haven't seen it at the Red Butte Garden, they're so gorgeous, huge, all fuzzy bees, so beautiful. I don't know if they sting though. Do they sting? The honey, the bumblebees? Do they? Yeah, yeah. I don't know. I feel like they're so serene. I want to get close to them, and anyway. Okay, yeah. And they're so anyway. I get stung. I got stung by a bunch of yellow jackets a month ago. Anyway, I'm at risk of an anaphylactic shock, so I had to. I have an EpiPen. Anyway, all right. So you take that little stick, okay, and you dip it on the honey because you want to taste it, okay. So what happens when you take it out? When you take it out, that little stick. Let's suppose this is the stick. It's gonna have some honey on it, right? So some honey is supposed to kind of look like this, and then it's gonna start dripping, right? So the honey is gonna stick. It's gonna on both sides, sure, right? But it's gonna kind of stick out like this, right? And then it's gonna drizzle down, okay? So now the question is, just using mass conservation, so using mass conservation, using mass conservation, find the rate of change, or find how this width at the bottom, we're going to call that B of t, find how B of t changes over time. So we're going to idealize this a little bit. We're going to draw the stick. Okay, we're going to assume the length L. It's like that joke about the physicist who assumed that the chicken is a sphere and then did the analysis on how the chicken moves. Okay, so we're going to assume this is this honey looks like a this nice triangle over here. At the bottom, the base is B of t, the length is L, okay? And you are given actually the velocity profile over here. So at the bottom, the velocity looks like, I can draw it top of this, but okay, so let's say, so the velocity over here looks like it's linear and looks like this, okay? So u at the bottom is equal to some u times y over b of t. Y is this axis, okay? So u at the bottom changes, goes from 0 to a maximum value according to this formula. This is a constant, whatever in the example is 10 to the minus 3 meter per second, but it doesn't matter. We're going to do all of this symbolically. So we know the velocity at the bottom, and this is still b of t, okay, the base. All right, let's do this. D by dt, partial by partial t of integral over the control volume of rho dv plus integral over the control surface of rho u dot n ds is equal to 0. What is our control volume? Probably the best control volume is this triangle, just where the honey is. Okay, we're just dealing with the honey. There's no flow going in, okay, on either side. The only flow is leaving through this bottom surface, okay? So Let's do this. The time-dependent integral is d by dt. Don't overcomplicate these examples, right? By saying, oh, well, you know, the control volume is moving and there's a velocity in this direction. So don't overcomplicate that way, okay? Especially with the exams, etc. Unless I specifically tell you, then you know, do not neglect like the velocity over here. I would give it to you, okay? Because in real life, you're gonna wanna need to measure something, right? You would say, okay, if this is gonna be an important velocity over here, then I need to measure that somehow, and then try to do the balance, okay? So in practice, when you're designing an experiment, for example, or doing some research, you probably would write this equation, do a control volume, expand all the integral, and say, okay, what am I missing? What information am I missing? Let me go measure that. Okay. D by dt of integral over the control volume. So this is our control volume, right? It's this triangle, okay, of rho dv. That's equal simply to d by dt of rho times the volume, because the density is constant, and the volume is, so you get rho d by dt. What is the volume? It's the base times the height over 2 times, you know, a unit depth per se. D by dt, rho d by dt of b of t times L over 2. So that's 1 over 2 rho L dB by dt. Okay. The second integral over the control surface, rho u dot n ds. Again, approximately the only surface that matters is this surface at the bottom. So that's going to give us the integral from 0 to b of t of rho. Now u dot n, u is coming out, n is leaving, so they're positive. So you simply get u times y over b of t dy. Okay. So note the bounds of this integral. That control surface is shrinking over time, right? Because b of t is shrinking. So you're integrating. So if this is b of t, right, and the velocity looks like this, well, b of t is changing over time, right? So you're carrying this integral from 0 to this point, which is b of t, okay? So it needs to be a function of time. So with that, the only quantity that matters here is y, which is really nice. So you get rho u over b of t times y squared over 2, and you're going from 0 to b of t, right? So you get rho u over 2 b of t, because this gives you b squared and simplifies with b, so you get rho u b of t. Finally, you combine the two and say 1 over 2 rho L dB by dt plus 1 over 2 rho u b of t equal to 0. 1 over 2, 1 over 2, rho and rho, they simplify. And you get an equation for b. So you get dB by dt equal minus u over L b of t. Okay. So notice the rate of change. So b is a positive quantity, but its rate of change is negative. Okay, it means it's shrinking, right? That distance over here at the bottom is changing in time and it's shrinking. Hence the negative sign over here. Okay. The solution in this case is v of t is some initial, the initial thickness of the honey, b0 e to the minus u over L times t. So there's exponential decay for that thickness. So contrast that with the height, how the height of water is changing. The height of water is changing linearly over here, but over here it's not linear, okay? It changes exponentially. Now, this is partly due to the fact that the velocity profile is not uniform. It's a function of y, okay? So that gives you the y squared term, which in turn, you know, gets b squared and b, they simplify, okay? So have you all seen this kind of stuff in undergrad, in your undergrad fluids? Okay. I just want to know because we all come from different educational backgrounds. I had 5 courses of fluid mechanics in my undergrad. These people who taught me were extreme, like on fluids. So, you know, but here at the U, we teach 1 course on fluids. Okay, and so I don't know what institution you're coming from. So it's good to gauge where you're at. Have you seen this level of work done in your undergrad? Okay. So this is sort of new to you. Okay. But it's gonna start making sense. Okay, good. Okay. Hopefully we all get on the same page. Okay. All right, now the next step. So when you think about the structure of how I want to teach, I'm teaching the course, we put in a framework for how we want to study the alien fluid mechanics, the fluid, okay? And that was to apply the great conservation laws. We listed those: conservation of mass, conservation of momentum, conservation of energy. And then we wrote the equations, but we realized that those equations, they apply for a system, not for for just a blob of fluid, right? Not very useful for us if we want to inspect the fluid flow at every point, etc. So we took a detour. We looked at what's called the Reynolds transport theorem, which gave us this nice translation from the system description to the Eulerian description, Lagrangian to Eulerian. Remember, all the great conservation laws are written in Lagrangian form. They apply for a system, well-defined, identifiable unit of quantity of a material or something, okay? So we did the Reynolds transport theorem. That was general enough. And then the next step is to take that Reynolds transport theorem, apply it to each one of those conservation laws. In each conservation law, we're going to look at the integral form, the Reynolds transport theorem, but we realized that it wasn't very useful in identifying what happens inside the fluid flow itself, like velocity profile, turbulence, you know, other things like that. It's not helpful that way because it's an integral form. It gives you a big picture idea of what's happening in your fluid mechanical problem. So what we're going to do next is look at the differential form of each conservation law. So we're gonna do the integral form of mass, and then differential form of mass conservation, integral form of momentum, and differential form of momentum. Okay, and if we have time, we'll do the energy equation. Okay. So next natural step is to do the differential form of mass conservation, what we know or what is known as the continuity equation. Right. So differential form differential form of continuity equation. Differential form of mass conservation. Let me put it. Of mass conservation. Okay. So for mass, we said that the mass system by dt is equal to 0. And then we wrote that as d by dt of integral rho dv over the control volume plus integral the control over the control surface rho u dot n ds equal to 0. There's something really nice here in this integral is that the right-hand side is 0, and you have integrals on the left-hand side. Okay, we need a way to eliminate this integral. We just need an idea or a thought process, a logical, rational process to eliminate this integral. There are two issues here. First, so say, how do we eliminate the integrals? So if we eliminate the integrals, I claim that we will get a differential form. So imagine you just remove the integrals, you're going to get a differential equation, and you're done. Okay, but there are two problems, two issues. Can you think of one issue? At least one issue.
If we eliminate the integral, there will be a constant.
The constant? No. No. Yes.
One of them is we have different intervals. One of them is in control volume, and
Yes.
the other one is
Okay. Issue one. Good. So issue one. So your colleague is saying that these integrals are not of the same type. Now remember, I alluded to that earlier when we were doing the divergence theorem, etc. It would allow, I said it's going to allow us to convert integrals of different types. Okay. So the first issue one, integrals are of different types. One of them is a surface integral, and one of them is a volume integral. The second issue what do you think? I have this d by dt outside the integral. So if I want to write everything here under an integral, I need to be able to move everything inside the integral and make sure that all the integrals are of the same type. So the other issue is this d by dt. How do we convert that into an integral of d by dt? Okay. All right. The first issue can be easily solved by using the divergence theorem. And that is the integral over a control surface of rho u dot n ds, remember, is the integral over the control volume. And it's that same control volume, right? Because the control surface corresponds to the surface of this control volume. So it's the same volume, okay, of div rho u dv. Remember that? We spent a lot of time on that early on. So that was why it's important. Okay. What about the d rho by dt? If the control volume is fixed and not changing in time, which is the case for how we started doing this analysis, then simply d rho by dt goes inside the integral because the bounds, the control volume itself is not changing in time. So there's no change in time for the control volume. Now, this will still work even if the control volume is changing in time. The math gets a little bit more complicated, but still give you the same identical answer. So what we're going to do is simply say that assume control volume is not a function of time, doesn't change over time. So the control volume is fixed region in space. That's kind of how we started, right? So then this whole equation turns into, I'm going to write it in red over here, integral over the control volume of d by dt of rho dv, okay? Or d rho by dt of d rho by dt dv plus integral over the control volume of div rho u is equal to 0. So now we can put all of those under the integral sign. Integral of over the control volume of d rho by dt plus div rho u dv is equal to 0. Okay? Almost there. So we know we have a differential equation inside, but we still have the integral. But the great thing is that the right-hand side is 0. So what I'm going to claim is that this implies necessarily that d rho by dt plus div rho u is equal to 0 because the control volume is arbitrary. So for this to hold for any control volume, we never said what our control volume was, correct? When we derived this conservation law, I didn't tell you the control volume has to be a 1 cubic meter cube, right? I didn't say anything. Control volume could be anything, any shape you want. So it's arbitrary. For this integral to hold for any control volume in the world, any control volume that you or you or you or you or me specify, then the necessary and sufficient condition is for the integrand to be identically 0. For this integral to be equal to 0 for any control volume, for an arbitrary control volume, then it is necessary that the integrand is equal to 0 in and of itself. And that's how you derive the differential form of mass conservation, which is also known as the continuity equation. Okay, you might be still skeptical about this. It's one of the greatest leaps that is done in this between this integral and differential analysis. But worry not. We will derive the continuity equation directly from a shell analysis, okay? Differentially, without doing any integrals, okay? All right, I hope you learned something today. I'll see you on Friday. So there is a graduate activity that GSAC is organizing that. Professor Hafner mentioned